All right, let's do this. Today, we are pulling back the curtain on the most powerful tool of our time, the modern computer. We're going to get right into it and demystify this incredible machine, breaking down how it actually thinks.
Have you ever really stopped to think about it? You click a button and this whole universe of information just appears. How in the world does a machine that's basically made of sand and metal understand what you want and deliver it in like the blink of an eye?
Well, the answer isn't some single magic chip. It's actually a whole series of incredibly clever engineering solutions stacked on top of each other. Think of it like a tower of brilliant ideas. Each layer solves a problem, which then creates a new foundation for the next big idea to build on.
So that's what we're going to do right now. We're going to take a journey. We'll start with the big picture and then zoom all the way in, peeling back the layers to see how a computer really, truly works. Okay, so our first stop is the most fundamental concept of them all. What is it that makes a computer a computer? How can this one single box on your desk be a calculator, a movie player, and a way to talk to someone across the planet all at the same time? The secret sauce is in how it handles instructions. And to get that, we have to ask a really basic question. At its core, what even is a computer program?
It's really just a list of instructions. And the absolute game-changing idea, which we credit to the mathematician John von Neumann, was the stored program computer. Here's the brilliant part. Instead of being hardwired to do just one thing, the instructions, the program itself, are stored in the exact same memory as the data. This means if you want the computer to do something new, you don't change the hardware, you just change the program in its memory. That single idea is what makes computers so unbelievably versatile.
And this whole architecture, it rests on three simple pillars. First, you've got the memory. This is where everything lives. Your programs, your data, all of it. Then you have the central processing unit, the CPU. That's the brain, the part that actually reads and follows those instructions. And finally, you have input-output, or I/O. That's our window into the machine. Our keyboards, mice, and screens.
Okay, so we've established the CPU is the brain. But how does it actually think? Let's zoom in a little closer and look at the fundamental rhythm of the machine. You could almost call it a heartbeat.
Believe it or not, the CPU's entire job boils down to a super simple, endlessly repeating loop called the fetch, decode, execute cycle. It fetches an instruction, it decodes it to figure out what to do, and then it executes it. That's it. The magic is that it does this millions, sometimes billions of times every single second.
So let's break that down. First up is fetch. The CPU has this special little pointer called the program counter. The easiest way to think about it is like a bookmark in a book. It always points to the exact memory address of the very next instruction it needs to grab.
Right. Next is decode. So once that instruction is fetched, a part called the control unit takes over. Its job is basically to be a translator. It looks at the raw binary code of the instruction and says, aha, this means add these two numbers. And then it gets all the right circuits ready for action. And finally, execute. This is where the work actually happens. The control unit gives the green light to the arithmetic logic unit, or ALU, to do the job, whether that's adding two numbers, comparing them, whatever. And as soon as it's done, the whole cycle starts over for the next instruction. Fetch, decode, execute, over and over. Now, let's zoom in even further, right into that execute step, and specifically the ALU. You would think that adding two numbers is the absolute simplest thing a computer can do. But when you're doing it billions of times a second, even the tiniest delay can become a massive problem. And it turns out there's a fundamental issue with the way we all learn to add in school.
The problem is carrying the one. See, the simple way to build an adder circuit is called a ripple carry adder, and it works just like we do on paper. To figure out the sum of the second column of digits, you have to wait to see if there's a carry from the first column. That creates a delay that literally ripples through the entire calculation. The solution? A much more clever device called a carry look-ahead adder, which, just like the name says, predicts all the carries at once. And get this is not a new problem. The computing pioneer Charles Babbage saw this exact bottleneck way back in the 1800s for his theoretical machine, the analytical engine. He knew that waiting for the carry to ripple through was a major roadblock to making his machine fast.
So how does this magic carry anticipation actually work? Well, it uses two simple ideas. The first one is called generate. The circuit looks at a pair of bits, like 1 plus 1. It knows that 1 plus 1 will always generate a carry to the next column, no matter what. The logic can spot those situations instantly.
The second concept is called propagate. Now, a pair like 1 plus 0 won't create a carry all by itself, but it will pass a carry along. It'll propagate it if it gets a carry from the column before it. So by combining the logic for all the generates and propagates at the same time, the adder can look ahead and figure out the final result pretty much instantly, in parallel. It is massively faster.
Okay, so we found a way to make a single instruction faster. Now let's zoom back out. How can we make the flow of many instructions faster? Well, it turns out the answer came from the factory floor. The big idea here is called pipelining. Instead of making the processor do one instruction completely from start to finish before it even looks at the next one, you treat the whole process like a factory assembly line.
So with this method, just as the first instruction is moving from its fetch stage to its decode stage, the CPU can already start fetching the second instruction. As one moves down the line, another one enters, so once that pipeline is full, the computer is actually finishing an instruction on every single clock cycle. It's a huge speedup.
Now, of course, it's not always quite that perfect. Sometimes the whole assembly line has to hit the pause button. This is called a stall or a pipeline hazard. It happens when, say, instruction number 4 needs the result from instruction number 3, but instruction 3 isn't finished yet. This forces the pipeline to wait, which briefly slows things down until that data is ready to go.
Okay, so we know how computers process instructions and how they deal with whole numbers. But what about everything else? How does a machine that only really understands ones and zeros handle fractions, decimals, or the ridiculously huge and ridiculously tiny numbers you need for science?
Well, there are two main ways to do it. The first is called fixed point. It's simple and fast. It just decides ahead of time that the decimal point is always in one specific spot. This is fine for something like money, but it has a really limited range. The much more powerful and common method is floating point. This is basically just scientific notation but for binary numbers. It stores a number in two parts, the main digits, called the mantissa, and then an exponent. This allows the decimal point to float around, letting the computer represent a truly incredible range of numbers, from the microscopic to the astronomical.
This whole system is so important that it's actually standardized. It's called the IEEE 754 protocol. It defines different levels of precision. You can see that by using more bits, going from 16-bit half precision all the way up to 128-bit quad precision, the computer can dedicate more space to both the exponent and the mantissa. And the takeaway here is really simple. More bits means you get a bigger range and more accuracy.
So there you have it. From the core idea of a stored program computer, to carry look-ahead adders, to pipelining, to floating point numbers, we've really journeyed through the clever tricks that make modern computing possible. And you can see how each idea built upon the last one, solving some fundamental problem of speed or representation. It just kind of leaves you wondering, right? What's the next big bottleneck? And what brilliant idea is waiting just over the horizon to solve it?